residues or high temperature residues is very tough to get it. So in this application you get up to 720. Beyond that you will get a residue only.
But the issue should be starting from 100 to 1.
Or a temperature setup which can liquefy these gases also, so that you can get it vaporized here and get low loss of the C3 or C2 hydrocarbons. If you have a 25 or 30 degree room temperature or inlet temperature, starting temperature, so what is the mean of getting this inlet?
Right.
It will get lost without entering the inlet point. So you have to provide a -20 or -10 degrees Celsius at inlet point. For that you have to be a nitrogen provision. But in this our instrument we have only from C5 onward only. So C5 onward we can get easily. So getting as per application now, your hydrocarbons or your crude hydrocarbons can have components starting from C1, C2, C3 and up to C60, C100 it can be there. So if your application must be inclined in the way that you have to significantly get your data separated, because this is a separation technique, no? So you get, if you are having or dealing with a LPG or naphtha fractions only, so you have to go only C10, C12 or C13, 15 only. So what is the need of go to up to C100? Or if you have a C60 or C80 data only, C80 hydrocarbons only, then it is no need to get the GC beyond this C2, C3, C3, because there is no signal there.
So basically, what are we going to feed here as a sample?
I'm showing you.
Either the crude oil or the...
Any type of sample, just like this is a pyrolysis oil sample, which get here to get analyzed, and what are the hydrocarbons is there, which type of boiling point hydrocarbons are there. So we get only boiling point and volume recovery data.
Is there any sample preparation, like filtering your sample through a point of 4 or 5 micron? Okay.
I'm coming on that point of.
There is no any other information about this sample except pyrolysis sample.
Any type of sample.
No, you are two phenomena. When IDP remains below 615, and another one is 615 to 700 Celsius temperature.
100 to 615. It is a one ASTM application. It is known as 7213.
Understand? Two methods.
Two methods
That
we
is
are
just
having
two
here.
methods.
We are having two
We
methods here.
don't know the range of this sample. and this
No,
sample.
it is not known to us.
It's unknown.
It is unknown to me.
Which method will first apply?
I will apply 7213 only because it will cover 100 to 615. And our user then told us that it is a pyrolysis oil sample, and his or her aim to provide a pyrolysis sample within a range of diesel, or its final application is to get diesel with this pyrolysis application. So this sample must lie beyond
650.
this range, in this range. So I will run this sample and it will get the data according to the calibration mixture, which type of hydrocarbons are converted. So with this RT correlation, I will get the data for this specific sample. C5 is there, C8 is there or not, C20 is there or not. That data only we can get according to boiling point.
Yes.
So shall we start with instrument basics first, no?
Yeah. So I had a question about the in here gas, but why you need to sample is oil? The sample is oil.
This is basic. Now
Yeah.
I will start with instrument, and then I will start with instrument. You will get resolve your query.
Yeah, this is here. Yeah.
Okay.
So I have a question.
Please ask.
The sample.
So what? Assume now you have.
This is a normal sample.
Okay.
Oh.
Assume now you have given a sample. Sample come to laboratory. Before you do this GC techniques, what are preparation you have to do with your sample?
I will do now. I will tell you all the points. These are getting you early on that points.
Thank you.
You know the GC?
Exactly.
Name me the three parts of GC.
Gas.
There is a auto sampler. There is a
Auto
oven.
sam-
Auto sample. This. part.
This is auto sampler. Yes. Next.
Yeah, there is a GC. No. Oven. there's
Oven. Column.
detector.
Okay.
BMS,
Which type of detectors
there is a
can be used?
FID,
FID.
there is a MOS,
MOS.
mass
Mass is MS.
Yes.
MS, mass spectrometer.
There is the ICD,
ICP.
SPS.
ICP can be used. So these are the different techniques. So I will just, before getting your query, I will just brief this GC also with these points you have mentioned. Okay, there is a auto sampler. It is connected with this inlet point. This is inlet point.
You give me the
I will
paper.
just demonstrate and come to your point.
okay.
Because many of you have seen or heard or learned what is GC is, but some of may not be aware that what is the basic parts, how the GC look like, how the column look like. Some have studied but some have not seen, and it's my duty to show you how the GC and column look like. Okay, so this is our auto sampler. This is our inlet. So inlet connected with this column. So this column part connected with this one end connected to the inlet, and another part is connected to the this is outlet point is connected to the detector part. Here we are using FID, flame ionization detector. It can be TCD, it can be MS or some other detector type you can also use here. But here for our application we are using FID as a detector. This is our column, 5 meter length of column. This chamber is known as oven, in which column is hanged, and this hanged column is used to separate different components of our sample,
Simple.
which run through this inlet point to detector point in a gaseous mode or a vaporized mode. So whenever you get a sample in liquid form, in solid form, or in gaseous form, you have to enter from inlet. So before entering inlet, you have to dissolve it in CS2. So what is CS2? Carbon disulfide.
Carbon dioxide.
Carbon disulfide, CCl4, anything solvent you can use to dilute and prepare your sample. So when you prepare this sample will become like this. So this sample is a diluted sample of that one. You are having this in this boil.
Volumes you take to dilute? How many volumes?
What's the
Just
dilution?
I'm coming. So a concentration is not known to you. Either it is a dilute, either viscous, how much viscous. So you will prepare a 1 to 2% of this hydrocarbon with the help of CS2. You run a CS2 as a blank also.
Yeah.
So whenever you run CS2 as a blank, all the previous signals will nullify and you get a blank baseline. After that baseline, and with the help of this calibration data, you run this sample also, diluted sample. And the must thing you have to notice before preparing a sample inlet injected to your GC, that its sample is 100% or a highly soluble in this your solvent medium, whichever is used in the blank also. Solubility is must. So in CS2, most of the polar solvent get dissolved. So we use CS2 here. You can use any one depending on your sample conditions. The solubility is must there. So we prepare this sample 1 to 2% only. We get enough intensity of every hydrocarbons. So that's why we are optimized 1 to 2%. Till there, any query? This is sample preparation. Till sample preparation, we have it.
Do you just make the dilution or do you filter through any micron of filter?
We can do filtration also, but here we are using only hydrocarbons. The pyrology samples we are getting, it is also hydrocarbons. Because you have heard one term cracking there. In whenever you discussed distillation, two boiling point distillations, there is a cracking term you have heard. So what is this cracking basically? Because sometimes we have to need to do this cracking, and sometimes we have to avoid it.
Breaking up the higher hydrocarbons into lower one.
So breakdown of your higher molecule hydrocarbons to get a lighter fractions or lighter molecule hydrocarbons is the cracking process. So thermally it is happening whenever you do distillation in atmospheric conditions, then cracking can happen. So to avoid cracking in distillation part, you will do a vacuum distillation to perform a higher boiling point at a lower boiling point under reduced pressure distillation. So but whenever you required when you are getting a very high residual feed and you have to derive diesel, naphtha or some lighter fractions from there, you will do catalytic cracking, thermal cracking, and some wisp breaking process are there, which you have, I think, heard in your lectures also with YK Sharma sir. You have heard these terms. So what will happen? We crack the molecule, either wisp breaking, either catalytic cracking, either thermal cracking we can do. So we will, our final motive is to get a useful commercial products. Either it is diesel, gas oil, petrol, anything. So this is our final motive. So but here in this technique, cracking not happens because it is also in a vacuum conditions. Okay. In pressure condition we are doing it. We are using 3 type of gases here. One, red color mark, it is a hydrogen. Second one is helium. Third one is air. These 3 gases have different flow rates in running this from inlet to detector through this column. This column is made of fused silica column, as sir already discussed and told. In this GC a separation technique, we required a gaseous phase. We are using a gaseous phase to separate out through a stationary solid support. So what is this solid support? Here we have fused silica column, but what is the support? It is a PDMS, polydimethyl siloxane. It is a polymer, a silicon polymer, which have different polarity, and by this polarity each hydrocarbons get attracted with this polar bonds and bind a little bit, not permanently, temporarily bound on the surface of the PDMS molecule, and according to their flow it will lighter will come first to the detector, and then higher, then highest molecule hydrocarbon in the sample will reach to the detector and get detected.
Is hydrogen or
So what is the role with these gases? I am asking to you.
you have hydrogen, which
Yes.
is to basically burn your FID.
Huh.
You have helium as the carrier gas, and air is also what you need for the FID.
Helium is not used as a carrier gas, as sir already mentioned. These are 3 gases. There are 3 roles of these gases.
So you have
First, hydrogen. Hydrogen is used as a fuel. Fuel for FID. So it is roll only on FID. So you can see it line is connected only on FID. This line is for FID only, and this is connected with this your hydrogen line. Hydrogen is used for as a fuel to burn your hydrocarbons, which get separated and burned at FID. How will FID will detect? It will, you all have to study it yourself, because detector part, everything is analysis point of view. You every element or every hydrocarbon has some flame and some wavelength on that flame. So detector will pneumatically correlate with this wavelength number or wave number. Then this is a C5 hydrocarbon. This is how much intensity will get. So that will studied by FID. But we will correlate with our calibration mixture, which we have earlier run on GC. So our helium is continuously flow, so it will get your environment or inner environment during your sample running, or it is standby mode. Every time helium will get run with a very less flow rate, 20 or 35 ml per minute. It will run continuously to provide inert atmosphere. And what is the role of air? It will work as a carrier gas. What is the role of carrier gas? Whenever you inject your sample, it will get evaporated, and by the help of this carrier gas,
Air,
it will.
using air as your carrier gas.
Yes, yes, we are using air as a carrier
Air.
gas.
Strange. I know normally is that you have nitrogen, you have helium, and you have the
Air.
Inert gases especially.
So
It
we
is
have
not. It is not that air you are feeling
know,
surroundings.
it's-
It is a high purity air gas. And what is
You
the
also-
difference?
Because you also need, I mean, with the FID, it's a combination of air and the hydrogen to burn. And based on this, I would assume that the helium, because you'd want your carrier gas to be
Air will come with sample.
Inert.
Air will come with sample to detector point, na? Not here only. It is assume that it will come here and here only. It will go through the column up to detector. There is hydrogen is also there. Hydrogen is also there. So zero air continuously flowing, but its main role is to carry sample also. It will burn along with hydrogen here in at detector point, but it will carry the sample also along with.
The sample is carried out as vapor phase or liquid phases.
That point I will discuss, because here we have 1, 2, 3 points. Detector is stable at 375 degrees Celsius, so temperature is fixed here. We have programmed temperatures at inlet point and oven points. So what is this programming or temperature programming? Here we in start, inlet is at 100 degrees Celsius, and it will final temperature goes up to 375 here.
Okay, here 375. Okay.
But oven it is initially 40 degrees Celsius, and it will also go up to 375. This detector is stable at higher temperature 375. 100 initially, 40, 375. Due to these temperature gradients, when your sample is in liquid phase and it will get injected in your inlet point, it will get vaporized. So vapors will form. Then it will get a lower temperature. Then it will stabilize there. And after that, due to the flow of gas, it will slowly move to the column. And due to the PDMS or the polarity of your column matrix, every components of your sample will get separated out. Similarly, there is a high temperature, so tendency of gaseous molecule is to reach there and get detected. Programming. In programming,
Why burning is required?
burning is required. How will you detect which type of hydrocarbon is coming? We are using FID as detector. So FID is required burning.
only flow,
As
only
you
flow.
Already told earlier, the column is absorbing that molecule, and lighter molecule passing through the.
I'm not
column.
absorbing it, attaching to the molecule.
Yeah, what it is. Yeah.
It is not I told not permanently. It's temporarily
Temporarily.
bound to the surface.
Okay.
Because if it has a different components, everything will bound. But which will bound more?
Heavier will bound more.
No. Polar will bound more.
Polar.
Polarity. There is some terms, some chemical terms are there. You discuss all together also how polarity will affect the attachment your molecule here, because it is not permanently attached. Some terms are absorbed, adsorbs. These are some different there. So these are some basic terms. So whenever the molecules will come, it will attack like dissolve like. Means if your column is polar will attach and non-polar will move away. Similarly, less polar also will follow. So which have a less polarity, it will go first. So that's why. Programming of temperature. In programming of temperature, initially it is 100, it is 40, it is 375 is stable. I will let you know why 375. So similarly, there is a ramping is shown. So ramping, what is ramping? Initially it is a initial temperature 100, it will rise with 15 degree per minute. This is a rate at which this inlet and oven will rise its temperature. So rising this temperature, the final temperature will come as a detector temperature, this 375. So similarly, every molecule or higher molecule it is present, it will get a temperature of 375 and get evaporated either in a gaseous form, either in a liquid or gaseous emulsion form. It will get injected and then get to the detector. So what is the role of this simulation here? So in this simulation, with the help of a software, this data which we get area wise, as you seen here, as you see here, this is a sample data. So when starting from here, it will end here. So what it's shown, it show that some sample elution will start IBP at 365 and rise here, and FBP will this like. So how will this GC will detect IBP and FBP? How will this GC will detect IBP and FBP? Because in true boiling point in D86, we have first drop come out, we will notice it as a IBP will for sample. And how much is the maximum temperature risen during experiment? It is known as FBP whenever we do D86 or any destillations. So here we cannot notice any drop, we cannot notice any final temperature.
Okay, this is the curve.
So how will we measure the IBP, FBP?
This is the curve. The starting of
Because you
elevation.
have a
This is
standard.
IBB.
It's because
and
you
the
have
end.
a standard, and each standard will come out based on its retention time. And then you will now have your sample, which will also separate, and then you compare the standard, and then you know what is the boiling point for each one of those standards. And that's how
No, this is the basically getting confirmation of particular hydrocarbon basically, but it is not my answer. Whenever you get a result of this 0 minute to 25 minute run time, and in this temperature range, it will detector will get 375 maximum temperature. So this is a 100% area which we have received with this chromatogram. So with this help of this chromatogram, we have achieved a 100% area. But by this 100% area, when the elution will start, area will rise. So the 0.5% of that area is covered or marked as a IBP point. So, and again 95% or 95 maximum area. This is the area covered by this signal. This is a single peak hydrocarbon or Leo sample basically, a sample which have a IBP or in the range of 365 or 455 cut it is. So you can get start area from here to here. So by this area, 0.5% of this area is non-IBP. Well, you are using this is SIMDIS, and 95 plus area, it is known as FBP. So in this way you mark with the help of this area. Similarly, this sample is run actually on 375 only, and we are predicting the sample result with our application either 7213 or 7169. We report it as up to 615 or 720. So this will done for simulation, and what simulation is help us simulation detect if this sample is having lines of spectrum, line spectrum and some band you have studied. So every peak is made up of lines, and then it will come as a spectra. So this 40 to 375 temperature profile is then linked to your boiling application range. 7213 has 100 to 615. Then it will plotted on that simulation automatically, and you will get the result like this, that this data has this type of boiling point, IBP, this range, and up to 544. FBP is 90 degrees. After 90, it has FBP of 546. So this type of temperature is getting by the help of simulation software.
But excuse me, you said that the initial boiling point is the 5%.
0.5.
0.5.
0.5% only of this area. Of this area. This is a peak area, na? This is peak,
Okay.
and this is peak area. So this peak area, this is baseline. This below line is the baseline, not this one. This one is the baseline,
Okay.
and this baseline, this has the 100% area.
Okay.
This peak area is 100% by this. If you measure from here to here, so 0.5% of this area is noticed as IBP.
Yeah, 5% only.
And the final?
95 plus 90 up to 95 you have the this noticeable area na for this your peak, but beyond that there is something, it is known as FBP. After that,
So there was a reading for the 95%, and what is after this reading it will be the final.
yes, after that it will mark a FBP point also, because we cannot get any drop or any final temperature na.
Yeah.
So similarly with this DAT6 or TBP, you notice first drop, then you will measure the temperature and you notice it as a IBP, and the final temperature rises in thermometer during the experiment, it is noticed as a FBP point. So these are the 2 points noticed virtually there, but here it will run whole chromatogram first, then decide how much the area is there. There is a single peak. If it is a multiple peak, one peak is there, one peak is there, one peak is there, and then it will get whole area
100%.
of the chromatogram as 100%,
Yeah.
and 0.5 is IBP in then FBP. So it's not. So this is the way how GC SIMDIS or simulation GC method marking the IBP and FBP for that simulated distillation applications, because here in this Advanced Crude Oil Research Center this GC is used for getting simulated distillation or distillation profile only, but this GC can have multiple applications.
What software you have on your
I'm sorry.
system? ChemStation, OpenLab, or specialized software?
The same he done.
No, this is not. This is another test running.
So we have three gas supply.
Gas line.
Yeah,
Yes.
so three type. Heli and
Helium,
Yeah.
hydrogen.
Yeah.
First one is hydrogen,
Yeah.
then helium, and then zero air. The role of zero air is here to carry a sample to detector also. It has 350 ml per minute of flow rate for zero air. Helium is 20 and 35 is your
Why
hydrogen.
you are calling it zero air?
It has a less or a very less impurities of nitrogen and other impure gases. If you cannot correlate with this air as a simple air, you are
It has
getting
a specified specification.
99.9%.
That means it's clear, more clear than the
More
the
clear,
normal
more.
air.
Because in air we get mixtures of gases, na?
Yeah, carbon dioxide.
Anything can be there.
Yeah, heli is 100%.
Yes.
Password. 1, 2, 3, 4, 5. As an ESTM.
These are everything is mentioned here. है ना?
So yes, you have helium or hydrogen. Because from my understanding, the air would oxidize the column, especially at that temperature.
We are getting air also, na? You can mention here. Carrier gas here also. High purity oxidant also is used in the detector point. Compressed air is a gas under high pressure and
So the
support
air-
combustion.
The air is for the FID detector.
But here in system na, for our application point of view, we are getting along with it. So we carry the gas molecules of the evaporized samples also. See in our case, it is also mentioned carrier gas is helium and hydrogen can also be used. But here helium is used as per application for this PAC software na, we are using. That particular software for simulation distillation we are using here. You are also correct.
Yeah.
Carrier gases, and it will, if we use a compressed air, compressor air na, then it will corrode.
So using ChemStation.
Chem station we are using.
ChemStation as well
This is
as
software.
Software.
Which?
ChemStation is a software.
Yes, it is a software.
Like the app connection between this one and GC. The connection. Communication.
I have started this method and transferred this method conditions here to show only you what are the different parameters of gas we are using here. So actually we are using hydrogen 35, air 350 ml per minute, and it is not nitrogen, it is helium basically we are using to provide inert atmosphere, and it is flow rate is 20 ml per minute. Sometime with the manufacturer point of view, na, so we have to modify the gases also. Your point is valid, so that's why it is recommended to use highly purity geo air, not a normal geo or compressed air we can use here.
So you have the air in bottles, or do you use
We have
generators?
cylinders, motor cylinders.
We use generators.
Generators is used to get compressed air.
So you have the compressor here, but you also have the zero air unit that is connected to the compressor.
That is there, but we are not getting high purity for that, no. We get a moisture
We use the
content
peak.
in there.
So those generators, like the peak, it comes with the filters and everything built in. So
They
everything
are
is
there, but still we cannot trust. Although it is not certified, no, we have a different setup there. But to get certified things, we have to trust some vendors or some manufacturers of that gas, who will certify and test gases also. How much purity is there and what are the other impurities are there. So they will post everything. No? If I will get only one cylinder per month, so to get that purity, it will using $100 or $200, and someone is providing in $10. So what is the use of that wasting that $100? It's better that I will give.
So those generators that come with a validation certificate, where it shows the output of the nature of the air.
Every
and the
certificate has
hydrogen.
to be validate once in a year or once in a 6 months. Am I correct? In a forensic science. Everything has to be recalibrated. So calibrating, if your output is not too much, na, so getting or running that instrument or that facility is quite enough, not very tough basically. So concerning on that point, we will trust them and we will get a bottled cylinder first. Although we have the setup for compressor also, that setup or that air is used for another application. Where we use only oxygen parameters to be done with this type of this air. Surface oxidation we will do, then there we can use it, compression. So this is all about this DC and what parameters is shown here. These are the 3 parameters I have already mentioned. So in the software point of view, if you all want, I will just elaborate the software also. So here we will have file, run control, instrument, method. In this method, we have this method pre-built. If you have to change something in this method, you have to go in manager and then you have to modify these parameters also. If you have to some other application 7213 or 7169, you have to change it. It's parameter basically, and then it will go in this 7213. It will handle 25-minute runtime. After that, whenever you go to 720 degrees Celsius temperature, then its runtime go up to 35 or 40 minutes. So in this parameter, only the SIMDIS we will do. We have new and edit sequence, open sequence, save sequence, edit sequence. So what is in this sequence? As we are using auto sampler, so we can design our sequence. In this designing, what we will do, please not record it. These are our run sample. Okay? May I request on that? This
So
is
my
our run
software-
samples.
So my software doesn't have this stuff. So that's why your graph actually looks like that. So that's an additional application.
Yeah, only that's why I am just showing you this experiment only. But if you record, if you stop recording, then I will come to this because some actual points are.
Okay.
You have to stop recording, right?